Hello, welcome to CSC7013, Advanced Math for Computer Scientists. This is Brady Chen. So one of the important part of the RSA is the key generation. So remember, to generate the key, we need to create two prime numbers. And then based on these two prime numbers, we generate a number n by multiplying these two numbers. And then we generate the phi of n. We calculate the phi of n, which is the Euler's tortious function of n. So then we select one key and then we calculate the other key by computing the modular multiplicative inverse of the first key. So today we can actually try to introduce the algorithm that is used to calculate the modular multiplicative inverse of a number, of an integer. So here's the problem. Given two integers a and m, so we need to find a modular multiplicative inverse. We use the notation a to the minus 1 of a and the modulo n. And we try to find a b such that the a times b mod n is 1. Okay, so this is very important because in the RSA key generation, we normally select one key, which is the first one, a, and then the other key is the multiplicative inverse of a modular n. So before we discuss this algorithm, now first let's talk about some of the properties related to the prime numbers. Now, suppose a and b or a and m are relatively prime. Then we know that there are two numbers. There exist two numbers x and y such that the a times x plus m times y equals 1. Now this is the factor. This is always true. Now we don't prove it, but let's assume this is the factor. Okay. So based on this, we can easily find out the multiplicative inverse of a modulo n. Now if we, for a and m, if we can find two numbers x and y such that the a times x plus m times y equals 1, then we solve the problem. We actually find the multiplicative inverse of a modulo m. And how can we do this? Now, once we find the x and y, then we can actually apply the modular operation on both sides. Let's say this is the left side. We apply modular operation mod n. On the right side, 1 mod m. So we apply mod m on both sides. Okay. So now let's take a look at this. On the right side, 1 mod n is 1. No question, because if we divide 1 by m, then the quotient is 0 and the remainder is 1. So it is 1. Now on the right side, so we can take a look at each of the terms in this right side. Now the first one is a times x, okay? And the second term is m times y. Now remember, m times y is a multiple of m. So m times y mod n, what is this? It's 0, right? Because when m times y divided by m, then you got a quotient of y and you got remainder 0. So it is 0. So the second term going to disappear when you do the modular operation. So that's the reason why this statement eventually becomes this. Now what does this say? A times x mod n equals 1. So what does that mean? So that means x is the multiplicative inverse of a mod n. So we find out the multiplicative inverse of a. So if we can write, this statement, a times x plus m times y equals 1, then x is actually the multiplicative inverse of A, mod M. So based on this, we can calculate the multiplicative inverse of A, mod M, very easily. Let's actually take a look at two examples. So let's take a look at the first example. So let's find the multiplicative inverse A to the minus 1 mod N, when A is 17 and M is 60. So basically, we try to find, the multiplicative inverse of A, which is 17 mod 60. And what is this? Okay. Now, in order to make sure that the multiplicative inverse of 17 mod 60 exists, you have to make sure that the A and the M are relatively prime. And this is the case. You can check it very easily, right? So I'm not going to check this. So 17 and the 60, they are relatively prime. So in order to do this, here's the process. So what I'm going to do is, I'm first going to actually, divide 60 by 17. You divide 60 by 17. Now what do you got? So you will find out 60 divided by 17, you will get the quotient 3 and the remainder 9. I'm not going to do this. You can double check it. Okay. So then once you got this, so you got a 17 and the remainder 9. So now the next step is divide 17 by 9. 17 divided by 9, what's the quotient? The quotient is 1. What's the remainder? Remainder is 8. So now you got 9 and 8. 9 is the value and the remainder is 8. Now you divide 9 by 8. Okay. So what is the result? I got a quotient 1 and remainder 1. Now once you got the remainder 1, then you know that I actually find the multiplicative inverse of 17 mod 60. Now how can I actually prove this? So here's what I'm going to do. I'm actually going to do this in the reverse order. So first look at this statement. 9 equals 1 times 8 plus 1, right? So now this is the remainder 1. So what I can do is I can rewrite this statement as a 1 equals 9 minus, so I move this 1 to the other side, right? So 9 minus 1 times 8. Or I can write as 9 plus minus 1 times 8. What about this? So this is basically the same, but I just move one item to the left. And I switched order, so I put the 1 on the left. Okay, now we got this term. So I'm actually going to move, just move it further. So what is 8? 8 is the remainder when you divide 17 by 9, right? So I can actually apply the second statement. So now I have a 9 plus minus 1 times 8. And I replace 8 by 17 minus, I move this to the left, right? 17 minus 1 times 9, or I can say 17 plus 1 times 9. So I replaced 8 with this number based on the second equality, right? Okay, so now let's do this. So I can use distributive law and multiply this minus 1 into each of the item inside. Don't actually add together because I want to keep that form. So when you actually do this, you will find out, so this is actually going to be, here's a 9 and here's another 9. So the other 9 you can combine these two, right? So when I multiply -1 into the parentheses, so -1 times -1, that's 1, right? Times 9, so that's 1 times 9. And plus the other 9, what do you get? So you got 2 times 9, right? So this is a 1 9, this is another 9, because of -1 times -1, that you got 1. So I have 2 9. And then I can put this first one, -1 times 17, right? -1 times 17. So I got the -1 times 17. I got this. Let's continue. So we can actually continue to the top. So what is 9? 9 is the remainder when I divide 60 by 17, right? So I can actually do the substitution further using the first statement. So I got -1 times 17 plus 2 times 9. So I replace 9 with 60 minus this term. I move this term to the left. So, or I can just write 60 times plus -3 minus 3 times 17, right? So this is based on the first statement. Okay. Now let's take a look at further. So basically we have a 1 equals this, equals this, equals this, and so basically it's 1 equals this, right? And then I could just change the right side because I can combine the term 17. Okay, so here I have a -1, and here I have a -3 times 2, right? So I have a -6 times 17, and -6 times 17 plus -1 times 17. So what I got -7 times 17 plus 2 times 60. Don't multiply out, okay? So I got this. So 1 equals this. Now can you see what is the multiplicative inverse of 17 modular 60? It is -7, right? Because based on the fact we just talked about at the beginning of this talk. Now if you still don't see it, don't worry. So we can actually take a modular operation on both sides. I say 1 mod 60, and then I doing the modular operation 60 as well. So I put the modular operation on both sides. Okay. So I have put the modular operation over here, modular operation here. I got this. So 1 mod 60, it's still 1, right? When I divide 1 by 60, the remainder is still 1. So it's still 1. Now let's take a look at this modular operation. So it's a so that's the modular of this. And what's the mod operation of the second term? So 2 times 60 mod 60. What is this? It's 0, right? Because when 2 times 60 divided by 60, I got a quotient of 2 and the remainder 0. So it is 0. So the second term actually disappears after the mod 60. So what I get is -7 times 17 mod 60. So actually, so I can prove that yes. So 17 minus 17 times 7 -7 times 17 mod 60 is 1. So 17 is -7 is the multiplicative inverse. However, in the RSA, I want to find the multiplicative inverse of 17 within the range of 0 and 1 and 17. So I want to actually find the multiplicative inverse within the range of 1 and 60. Okay. So how to do this? It's pretty simple. Since 17, minus 7 is a multiplicative inverse of 17 modulo 60. So in order to actually find the multiplicative inverse of 17 modulo 60 within this range, what I need to do is just plus 60. Minus 7 plus 60. So what I got? I got a 53. Now 53 is the multiplicative inverse of 17 modulo 60. Can you verify this? I can leave that to you. So you just need to verify that the 17 times 53 mod 60 is 1. Okay. You just need to verify this. So that's the answer. 53 is the answer. Okay, let's quickly look at another example. So now in this case, we assume A is 21 and M is 880. So now, in order, before you actually try to find the multiplicative inverse of 21 modulo 880, so you need to first, verify that the A and the M are relatively prime. I'm going to leave that for you because you need to calculate the GCD of A and M, right? Make sure the GCD is 1. So suppose that's the case. So we want to find the multiplicative inverse of 21 mod 880. Okay, so what is this? Again, we follow the same process. So the first one you need to do is, let's actually divide 880 by 21. And then we try to find what's the quotient and what's the remainder. And the remainder is 19 and the quotient is 41. So you can verify this. And then we got this. Now divide 21 by 19. What is the quotient? 1. What's the remainder? 2. So 1 times 19 plus 2, that's 21. So then we're going to do again 19 divided by 2. Okay. What's the quotient? The quotient is 9. 2 times 9 is 18. Then we have 1. So now we got 1. So we're done. So the next step going to be we're just doing the reverse of this. Again, we just write to 1 as 19 minus, so we move this term to the left, right? So 19 minus, let's see, it's a plus minus 9 times 2, right? So 19 minus 9 times 2, so I put the minus sign inside the parenthesis. Okay, now the reason I'm doing this is because, so I should replace this 2, which is the remainder when you divide 21 by 19. Okay, so I can replace this times 2 is 21 plus minus 1 times 19. Again, I have a term 19, I have a 19, and that's the coefficient of the 19. So minus 9 times minus 1, I got 9, right? So now I have a 9 times 19 plus 19. So I got a 10 times 19, right? So I'm going to move this 10 times 19 over here. So And then what's the other term? Minus 9 times 21. Right? The reason I write this is because I am going to replace 19, which is the remainder when you divide 880 by 21, right? So let's go up. Okay, so we have a 1 equals minus 9 times 21 plus 10 times 19. I replace 19 with the first statement, so which is 880 plus minus 41 times 21, right? So I move this 41 times 21 to the left side, and so I put the plus minus 14. I put the minus sign in before the 14 and put it inside the parentheses. So again, we got 21 and a 21 here. Okay, so let's do this. So I'm going to put the 10 times 800, 10 times 880 here, and the first I'm going to put the 21 times, what is this? It's a minus 9. It's a 10 times the minus 41, right? So it's a minus 410, right? Right? So that's the coefficient of 21. So minus 9 plus, it's actually plus minus 41 times 10. So it's a 410. Okay. So which is minus 419 times 21 plus 10 times 81. Now what do you got? So I can apply the modular operation, modular 880. So on the left side, 1 mod 880, and on the right side, so 419 minus 419 times 21 plus 10 times 880 mod. Okay, I'm running out of space, so it's 880. Now again, the left side is going to be 1, right? Because 1 divided by 880, I got the remainder 1, quotient is 0. And this one, 10 times 880 mod 880, that's 0, right? Because 10 times 880 divided by 880 is 10, and the remainder is 0. So the quotient is 10, remainder is 0. So I only have first term left. So I have minus 419 times 21 mod 880. Again, this is the inverse of 21 mod 880. Since this is the minus number, so I want to actually, find the inverse within the range of 1 and 880, right? So want to make sure that it's within 1 and 880. So what I'm going to do is I just need to add, minus 419 plus 880. So what is this? I got a 461. Now, so minus 419 is actually multiplicative inverse of 21 modulo 88, but that number is actually outside the range of 1 and 880. So if I want to have a number between 1 and 880, so I just add 880. So I got this number. So this two number. So the answer is 461. Okay, so that's the answer. Now you can verify. How can you verify? Just 21 times 461 mod 88 to see whether the result is 1. Okay. So let's go back to the RSA key setup. Remember, as part of the RSA key setup, we need to first find the Euler-Tortue function of n. That's phi of n. And then we randomly select the encryption key, E. Okay. E could be public key or private key. Okay, it's up to you. So the E should satisfy these two conditions. One, E should be in the range of 1 and the phi of n. That's number one. The second one is E and the phi of n must be relatively prime. So that means that this GCD of E and the phi of n should be 1. Now, if this is the case, we know that it's based on the fact that it's guaranteed that there is a multiplicative inverse of E modular phi of n. In another word, we can guarantee to find another key D, which is a multiplicative inverse of E modular phi of n. Okay, so to find the D, we can use the approach we just did in the previous slides. And this approach is also called extended Euclidean algorithm. So we can easily find D such that E times D equals 1 modular phi of m, or E times D modular phi of n is 1. Now also, there's one note I want to point out is that when we use extended Euclidean algorithm, like the two examples we talked about, we may not be able to find a D such that the D is in this range. Many times we may find a D which is negative. So the negative is not in this range, right? If D is a negative, it's not in this range. But if a D happens to be in this range, that's great. So we accept the D as the other key, okay, the decryption key. However, what happens if D is not in this range? So for example, D is in a negative number, or D is bigger than phi of m. So then we need to do a little bit more job to force the D in this range. Now, how can we do this? Now, we need to know that if D is a multiplicative inverse of E modular phi of n, then we know that any number like a D plus phi of n is also a multiplicative inverse of E modular phi m. Okay, so it's also the E. Now, in fact, if D is a multiplicative inverse of E modular phi of m, now any number D plus k times phi of n is the multiplicative inverse of E modular phi of n. Now, I'm not going to prove this because the proof is pretty simple and pretty easy, right? All we need to verify is, so we need to verify that the D, if D times E, equals 1 modular phi of m, then we need to prove that D plus k times phi of n times E is also equals 1, right? Which is pretty easy to prove. Now, if that's the case, it's so easy to, find a multiplicative inverse of E modular phi of m within that range, right? For example, in the previous case, if D is negative number, so for example, if D is a negative number, then like a minus, so I think the previous case is that we find D, which is minus 419, right? And M is 880. Now, so D is not in the range of 1 and M, right? Now, how can we find a multiplicative inverse of the number which is actually in that range? It's pretty simple. So we can actually simply just, add the number by 880, right? Because that's the, that's actually D plus M. So D plus M is also a multiplicative inverse. Okay, now, so when we add these two numbers, we got what is the value we can get? It's a 461, and the 461 is between 1 and 880. So then we accept this as the other key. Now, if M is 880, and we assume that's the phi of n. So in that case, so if we actually use the extended Euclidean algorithm and we find the multiplicative inverse modular phi of m, which is outside the range, we can either, plus the phi of n or minus the phi of m. So we can easily, shift the value into this range. That's important. Okay. Thank you.